Could you actually create a black hole on Earth?
You wouldn't want to,
Okay.
but you could. Yeah.
Oh, you could.
Oh, yeah.
Oh, okay.
Yeah, yeah. And in a lab, I mean, in principle, you can create a region of matter so dense and small that it would classify as a black hole. What happens is small black holes evaporate, according to Hawking radiation. The small ones evaporate way faster than big ones.
Okay.
So if you make a tiny, mini, microscopic black hole, it might evaporate before it has a chance to eat the Earth.
Gotcha.
This is the monster of the universe. Imagine holding the power to create one of the most mysterious and destructive forces in our universe. An object so dense, so powerful that nothing, not even light itself, can escape its grasp once crossed a certain threshold. I'm talking about a black hole, a force so powerful and terrifying that we still don't fully understand it. But here's a question that might sound absurd at first. Could we actually build one? Believe it or not, this isn't just a theoretical question. Scientists at CERN, home to the Large Hadron Collider, have had to address public concerns about accidentally creating Earth-swallowing black holes. The fear was so widespread that safety reports had to be written and Nobel Prize winners had to make public statements. But why? Is there any scientific basis to these fears, or is it all just science fiction? The journey to answer this question takes us deep into the wild frontiers of particle physics, quantum mechanics, and general relativity. And along the way, we'll bump into some mind-blowing truths about the universe and what we're really doing here. Put on your best lab coat, because we're about to find out if we can build a black hole. To understand if we could build a black hole, we first need to understand what black holes actually are. At their simplest, black holes are regions of space where gravity is so intense that nothing can escape once it crosses what's called the event horizon. Not matter, not radiation, not even light. It's like a cosmic point of no return. Picture throwing a ball into the air. Normally, it comes back down because of Earth's gravity. Now imagine gravity so powerful that even if you fired a laser beam straight up, the light would get pulled back down. That's basically what's happening at the edge of a black hole. That boundary, the event horizon, is where physics, as we know it, starts to break down in the most fascinating ways. Cross that line, and you're literally erased from the observable universe. It's not that you'd just be trapped, you'd become part of the black hole itself. How do these monsters form naturally? Most black holes we know about form when massive stars, much larger than our sun, reach the end of their lives. When a star burns through all its nuclear fuel, it can no longer support itself against its own gravitational pull. For stars above a certain mass threshold, this collapse is unstoppable. The star's core implodes, squeezing all its mass into an incredibly small space. The gravitational field becomes so strong that it warps space-time to the point where even light cannot escape, creating a black hole. Then there are supermassive black holes, giants that sit at the centers of most galaxies, including our own Milky Way. These behemoths can have masses millions or billions of times that of our sun. How exactly these formed is still being debated. Did they build up gradually by consuming stars and merging with other black holes? Or did they form directly from the collapse of enormous gas clouds in the early universe? The answer is still unclear. But here, things get interesting for our question. Black holes can theoretically come in all sizes. While stellar black holes typically have masses at least 3 times that of our sun, some theories predict the existence of much smaller primordial black holes that might have formed in the extreme conditions just after the Big Bang. And this is where the possibility of human-made black holes enters the conversation. In the realm of particle physics, particularly in certain versions of string theory and models with extra dimensions, microscopic black holes might be produced in high-energy particle collisions. The idea goes something like this. Our universe might have more dimensions than the three we can see and touch. We all know about up-down, left-right, and forward-backward, the three dimensions we move through every day. But what if there are more dimensions that are somehow folded up or hidden from us? If these extra dimensions exist, gravity might behave very differently at extremely small scales. In our everyday world, gravity seems pretty weak compared to other forces. I mean, a small magnet can overcome the gravitational pull of the entire Earth when it lifts a paperclip. But in these extra dimensions, gravity might become insanely strong when you get down to subatomic distances. So what does this mean for making black holes? Well, if you could smash particles together with enough energy, we're talking truly astronomical amounts of energy concentrated in an incredibly tiny space, you might theoretically create the conditions for a miniature black hole to form. It would be unimaginably small, way smaller than an atom, but it would still be a black hole with all the mind-bending physics that entails. And this brings us to the Large Hadron Collider, LHC, the world's largest and most powerful particle accelerator. If you haven't heard of it, the LHC is basically a 17-mile circular tunnel buried beneath the border of Switzerland and France, where scientists accelerate particles to nearly the speed of light and then smash them together. When particles collide in the LHC, they create conditions similar to what existed just after the Big Bang, temperatures over 1 billion times hotter than the center of the sun. When they were building this monster machine, news stories started circulating that these high-energy collisions might create microscopic black holes that could potentially grow larger and consume the entire Earth. People filed lawsuits to stop the LHC from turning on. Some people were genuinely terrified that scientists were about to accidentally end the world. The fears got so out of hand that CERN, that's the European Organization for Nuclear Research that runs the LHC, had to gather a team of top scientists to address these concerns head-on. They produced a comprehensive safety report that was reviewed by leading physicists, including several Nobel Prize winners. Their conclusion? Even if the LHC somehow managed to create microscopic black holes, which was already a huge if, they would pose absolutely no danger to our planet. Why? For several compelling reasons. First, if such black holes could be created in particle accelerators, they would also be produced naturally when high-energy cosmic rays, particles from space with energies far exceeding those in the LHC, collide with Earth's atmosphere, the Moon, or other celestial bodies. The fact that these objects still exist after billions of years of cosmic ray bombardment is strong evidence that such black holes either don't form or aren't dangerous. Second, according to Stephen Hawking's groundbreaking work on black hole thermodynamics, microscopic black holes shouldn't stick around long enough to cause trouble anyway. Hawking showed that black holes actually emit radiation, now called Hawking radiation. But the smaller the black hole, the faster it evaporates through this radiation. Any microscopic black hole that might theoretically form in the LHC would evaporate almost instantly. We're talking about a lifespan less than 1/1000th of a second. That's so fast that the black hole would barely have time to exist, let alone grow or cause any harm. Third, even if, against all theoretical predictions, such a black hole somehow managed to be stable, it would still be harmless. It would be so incredibly tiny and have such a weak gravitational field that it would barely interact with ordinary matter at all. It would pass through the Earth like a ghost, similar to how neutrinos, these super tiny, nearly massless particles, stream through your body by the trillions every second without you noticing. So, after all that worry, what's actually happened? Well, the LHC has been smashing particles for years now, reaching energies of 13 to 14 tera-electron volts. That's tera-electron volts, a mind-bogglingly large amount of energy for particles, but still tiny in human terms. And guess what? No black holes, not even a hint of them. But that hasn't stopped physicists from wondering, what if we could create a stable, microscopic black hole? What would it look like? What could we learn from it? How might we use it? Well, one fascinating aspect of this question involves what physicists call analog black holes. While we might not be able to create actual gravitational black holes in a laboratory setting, we can create systems that behave mathematically similar to black holes and study their properties. Bill Unruh, a theoretical physicist, proposed in 1972 that a waterfall could serve as an analogy for a black hole. Take sound waves traveling in water, approaching a waterfall. If the water is flowing faster than the speed of sound in that medium, sound waves cannot travel upstream. They are trapped, just like light is trapped by a black hole's event horizon. Turns out, the math behind both situations is surprisingly similar. So, scientists have since created various analog black holes in laboratory settings. Some use carefully controlled water flows to create swirling vortices that act like spinning black holes. Others go even further, using super-cold Bose-Einstein condensates, where atoms behave as a single quantum entity, or special optical materials that slow down light to mimic black hole physics. Why go through all this effort? Because these experiments have actually let researchers observe things like an analog version of Hawking radiation. The energy black holes are predicted to emit as they slowly shrink and evaporate. While we can't exactly get up close and personal with a real black hole, these lab-made versions help scientists test their theories and get a glimpse of how these cosmic monsters behave. But what about creating an actual gravitational black hole? The energy requirements are huge. To create even the tiniest black hole, you need to squeeze enough matter or energy into an unbelievably small space. Physicists call this the Schwarzschild radius. It's basically the point of no return, where gravity becomes so intense that light gets trapped. For perspective, if you wanted to turn something as light as a paperclip into a black hole, you'd need to compress it into a space smaller than a single proton. We're talking about something already so small that millions can fit on the head of a pin. And you'd need to go way smaller than that. Our current technology doesn't come close to this capability. The Large Hadron Collider, impressive as it is, falls short by an absurd margin. The 13 to 14 tera-electron volts of energy it produces in collisions is approximately 1 trillion times too weak to create even the most microscopic black hole in our regular 4-dimensional world. That's like trying to launch a rocket to the moon with a slingshot. The only scenario where the LHC could possibly create black holes is if those extra dimensions I mentioned earlier actually exist exactly as some theories predict, making gravity super strong at tiny scales. And even then, remember what we discussed earlier. These would just be fleeting quantum hiccups that evaporate almost instantly, not Earth-devouring monsters. But hey, let's have some fun for a moment. What if, in some distant future, we developed technology capable of creating and containing stable, microscopic black holes? What might we use them for? Energy production is probably the most practical application. and it would be revolutionary. Black holes are nature's ultimate energy converters. When matter falls into a black hole, Einstein's famous E equals mc squared comes into play in the most extreme way possible. A significant chunk of the mass gets converted to energy in the accretion disk. That's the swirling vortex of superheated gas that forms around the black hole as matter spirals in. To put this in perspective, our best nuclear power plants convert less than 1% of mass to energy through nuclear fission. Even nuclear fusion, which powers the sun, only converts about 0.7% of mass to energy. But near a black hole, we're talking about potential efficiency ratings of 10%, 20%, or even higher. A black hole power plant would make every other energy source we have look primitive by comparison. That could power an entire city with something smaller than a grain of sand. Then there's the pure scientific value. Black holes are like cosmic laboratories where the laws of physics get pushed to their absolute limits. They're places where our two most successful but incompatible theories, general relativity, Einstein's theory of gravity, and quantum mechanics, our theory of the subatomic world, are forced to duke it out. These theories have been notoriously difficult to reconcile, kind of like trying to fit puzzle pieces from two different puzzles together. A black hole you could study up close in a laboratory might finally help us crack this problem and develop a unified theory of quantum gravity, what some physicists consider the holy grail of modern physics. And of course, science fiction writers have had a field day imagining even more wild applications. Need to get rid of nuclear waste or other dangerous materials? Toss them into your handy miniature black hole. Instant cosmic garbage disposal. Want to travel to distant stars? Some theories suggest black holes could power spacecraft by directing the intense radiation they emit. There's even speculation about using them to create wormholes, shortcuts through space and time that could potentially allow for faster-than-light travel. Are these ideas speculative? Absolutely. Some probably even violate laws of physics we currently understand. But hey, black holes are fascinating, terrifying, but fascinating. Even if we made it, even if microscopic black holes evaporate quickly through Hawking radiation, our understanding of this process remains theoretical. What if our theories are wrong? What if a created black hole behaved differently than expected? That's where imagination and the hunger for knowledge guide us to finally take the leap from theory to certainty. So could we build a black hole? With current technology, the answer is almost certainly no. At least, not a real gravitational black hole. The energy requirements are simply too enormous, and our ability to manipulate matter and energy at the required scales too limited. If we widen our definition to include analog black holes, basically systems that mimic how black holes behave mathematically, then the answer is definitely yes. Scientists have already built these analogs and are using them to test theories about black holes, especially when it comes to things like Hawking radiation. But overall, one thing is clear. We're not going to accidentally destroy the Earth with a black hole created in a particle accelerator. Well, at least not theoretically. Do you think humanity should even try to create a black hole if we could? Or are we messing with forces we barely understand? Drop your thoughts in the comments below. And if you enjoyed this cosmic journey, hit that like button and subscribe for more science explorations. Thanks for watching.